So this is the plan. None of this is very hard. So Amber Brown. She is my TA. And she is not here. Hopefully she's down there. I was like, is this Samantha's real name? But yeah, then I remember she's my TA. All right, polarity, hybridization, bond overlap. They're just little odds and ends we got to tie up. So if you would, we ended here yesterday. Will you quietly try and see if you can do this yourselves? So try to determine whether each one is polar or non-polar.
Did I nail it?
Remember the quietly part? I haven't had lunch yet, so you get hangry, Davidson. Even though I've had 2 bowls of cereal, 2 Mountain Dews, 2 cheese sticks, and some chocolate. Done? Done? Okay, who's done? Raise your hands. Okay, here we go. Let's focus here. I'm going to color all the polar ones this cute blue color. All right, so should I color this one cute blue? No. Should I color this one cute blue? Yes, I should. This one? No. This one? This one? Yes. This one? This one? This one? Yes. Wow, you guys are killing it. This one? Oh, this is a trick one. It's a yes. Now be careful. Be careful. This one normally would be a no, right? This one usually should be non-polar, right? Because it's symmetrical. What's tricky here? The note specifically said somewhere in here, if they're the same element, identical atoms, right? So since we switched up Cl and O, this would be slightly polar. Now they're not going to do that to you, I'm pretty sure, but it would be slightly polar because it doesn't have the identical element or atoms. Okay, so should I color it then? Yes. This one? No. This one? Yes. This one? This one? This one? This one? Are we all okay with the shape to polarity? No? What's that? Why is the last one polar? Okay, here we go. Because bromine and fluorine, we know fluorine's more electronegative, so there'd be a dipole going this way, a dipole going this way, and yes, those cancel each other out, but there's still one coming this way. So the overall electron density would move a little bit this way. Is it going to be like super polar? Not really, but it is definitely not one where there's something to cancel everything out. So like this one, which wasn't, we had a dipole this way, a dipole this way, a dipole this way, and a dipole that way. If I add all those vectors up, the electron pairs stay right in the middle. Go ahead, Seth.
So on the middle one is on the last row. Yeah. Sorry, the middle of last row. Yeah, that one.
Okay.
Is it non-polar for the policy else around it?
They're all the same, and it's symmetrical. Those are the 2 things you got to check. So like there'd be some pull up and some pull down, but there'd be some, they'd cancel each other out. There'd be a straight pull that way and a little bit that way, then angled, and a little bit that way and angled, and they all cancel out to be 0. Okay, fair enough. All right, so bond polarity from molecular geometry, manageable, typically not super hard. Okay. Just real quick, tell your partners. Is this one polar, nonpolar? Is this one polar, nonpolar? Okay, what shape is this thing right here? T-shaped. Those are typically polar, right? What structure is this? Linear. And these are typically nonpolar. Now I say typically because we got to check that they're the identical elements surrounding the central atom. But we had 6 here, and then that's how we end up with linear if we have 4 non-bonding around it, so forth and so on. Okay, I feel all right about that. All right, this is our goal today. These sound a lot harder than they really are in the test. So the term hybridization and hybrid atomic orbitals are used to describe the arrangement of electrons around a central atom. When the central atom is sp hybridized, its ideal bond angle is 180. For sp2, it's 120. sp3, it's 109.5. These are the things it expects you to know. It goes along exactly with what we've been doing. So usually kids are like, oh, okay, it's kind of weird, but that makes sense. Okay, and then this one's even weirder, but it's not that bad. Bond formation is associated with overlap between atomic orbitals. In multiple bonds, such overlap leads to the formation of both sigma and pi bonds. The overlap is stronger in sigma than pi bonds, which is reflected in sigma bonds having greater bond energy than pi bonds. The presence of a pi bond also prevents the rotation of the bond and leads to structural isomers. Okay, there's a lot there, but it really is not awful. I know I've said that 100 times lately, and you're like, you know what, Davidson, if you add up 45 not awfuls, you end up with an awful. All right, sort of like when your power goes out and you have an uncooked waffle. It's awful. Yeah, it was straight depression right there. Yeah, that's just disgusting. I'm sorry. I burn my waffles and then I like butter the crap out of them. I have a problem. Oh, I love that sentence. You're like my grandpa. That's what every middle-aged fat guy wants to hear. Thank you. All right. Okay. This will come together in a few slides. It may be tricky at first, but it's not that bad. Overlap and bonding. This really goes to the later part, but it has to be said here first too. We think of covalent bonds forming through the sharing of electrons in adjacent atoms. Like we've said this before. All right, we had hydrogen, which had just one, right? One valence electron. Then we had another hydrogen, and it had just one valence electron. And they form a covalent bond, that's supposed to be an arrow, when they overlap their S. Okay, they just take their S, their sphere, and it overlaps, and now both of them feel like they have 2. Okay, that's kind of the nuts and bolts of this. So in this approach, it can only happen when 2 orbitals overlap. All right, when they overlap, there's 2 types of overlap, and one is when the S's overlap, and one is when the P's, well, I guess there's kind of 3. We're going to learn about it, the third one later. But we have S's mixed with P's or P's mixed with P's. Just kind of stick with me. All right. So hold on, let me come here. That's out of order. Hold on, let me drag this. I was messing around and I didn't drag these high enough. Probably around here. Okay. So consider beryllium. Beryllium is element number 4, which means it has 4 electrons, which means if I were drawing the box like vertical, it'd be full right there, right? And there would not be able to be any overlap here. I wouldn't here anyway, because that's a core electron, right? There's no way we could have shells overlap because the only shell is full, but we know that things happen here. So what happens is in a reaction, a small amount of energy is absorbed and it promotes one of the two S's into a p orbital. So now beryllium has two places that it could form a covalent bond. You okay with that? When we do this, we call it a hybrid orbital because we mix it. Let me get rid of these. We've now mixed an S and one of the P's. No, it happens all over the place. So what we have here is a sp hybrid orbital. It means I have room to overlap one S and one P. Okay, let's look at another one. Maybe. Well, okay, we'll get there in a second. With hybrid orbitals, the orbital diagram for beryllium will look like this. The sp orbitals are higher in energy than the 1s orbital, but lower than the 2p. So it's a mix, and hopefully you're used to the word hybrid now because of cars. It's a mix between a gas and electric, typically. All right, it's where they blend the things together, and we call it an sp orbital. Okay, now boron. Boron is the S is full, then there's one in the P. But that would only allow for overlap of one of these boxes, right? But that's not what works. So what happens is boron in a reaction absorbs a tiny bit of energy and promotes one of its two over. So you end up with one in the S and two in the P's. And this hybridization is called an sp2 hybridization. Okay, if I were to draw boron trifluoride, do we remember it looks like this? Not distracting at all. It's fine. Not, I mean, not even remotely distracting. It's okay. So remember how boron trifluoride looks like that? Tell your partner how many electron domains boron trifluoride has. It has three, 1, 2, 3 places where electrons live, right? Everyone look at the screen. If you can put 1 in a hybrid S and then there's a 2, what does this add to? 3. This is a pretty simple concept. You will have to go from a formula to electron domains to a molecular formula to knowing the hybridization. If you know the number of, or if you know, the domains, then you will know the hybridization because the numbers always add to that domain. So we're going to do carbon next. In carbon, we have two places it could overlap, but that's not how it works. Carbon typically forms like CH4. It could only do that if it promotes one of these into this shell, and then it has 1, 2, 3, 4 places that overlap could happen. Kind of with me? All right, so in this one, I have an S, and then I have a P with how many now? 3. If this is a 1, 1 plus 3 equals 4. So I would predict this structure would be what shape? Tetrahedral, and it is, right? It's C, H, and then H, H, and like one's a wedge and one's a dash, right? And H. So the total amount here would be 4. My hybridization has to add to 4. Next, I had one more. For geometries involving expanded octets on the central atom, we must use d orbitals in our hybrids. So if I have 2, I promote 1 and I end up with sp P3D. All right. And that would mean how many domains? 5. 1 plus 3 plus 1 is 5. So what if I had 6? What do you think it'd be? And that's where we end. What's that? S will always be 1. It's always half of what it normally is. Because now we're talking about how many of them could share 1. So instead of 2s2, 2p6, it's now half of everything as it used to be. Because it's how many bonds it could form. Okay, so we have here our summary. So use your Lewis structure to determine the electron domain geometry. Then remember, you can only have 1s, 3p, and 5ds. Now, we never go past ds. There's actually really not a ton of proof that ds are even used in bonds still. We assume it, but we don't know it, even still in 2021. So we don't go anywhere past the D1s and 2s. Okay. The hybrid orbitals notation will always add up to equal the number of electron domains. No, it fascinates me too. I'm intrigued. All right, so let's go way back here and do something that I skipped. Where are you? All right, so we have C3H8. Will you draw the Lewis structure for C3H8 right here? Do it right now, Isaac.
He's trying to write his name right.
I can write my name left-handed. Here we go. On this slate, it's going to look awesome. There's my left-handed name.
That's better than mine.
Here's my right-handed name.
No, sorry, I was not worried about that. I was worried about my notebook.
It was sad. That's sad. Davidson's name is sad.
No. Oh my gosh. I have this big. Somehow I Tim stabbed me with a pencil in the second hour, and I started bleeding.
And Tim smiled. I still have pencil lead in my shoulder from second grade
Why?
because you have to dig it out. I got poked and it broke off.
We did it. We nailed it.
Nice job, Brown. He just went right here. Okay, about one more minute. If you are done with the structure, see if you could answer these two questions down here. The what?
The angle.
Oh, the angles. Okay, I'm moving on. Here we go. This one is really nice. This may or may not make sense to anyone. But if you have C3H8, I don't remember if we've talked about this or not, but if this is equal to 2x plus 2, where x equals the number of carbons. If this is twice as much plus 2, then they're super easy. It means there's no double bonds. Have I ever talked about that before?
No.
Okay, there's a language for organic chemistry and a very predictable everything. And one of them is this ratio. If it's 2x plus 2, it just looks like this. If it's 2x, it means you have a double bond. If it's 2x minus 2, it means you have a triple bond. But you don't have to know that. So anyway, we have 3 C's. And then all these are H's, right? Okay, then that was not hopefully that bad. Geometry of the central one. So we have just this one is the central carbon atom. So how many domains? It has 4. So what do we call that geometry? Tetra. Hybridization then of tetra. sp3, because tetra means 4, right? And this better add to 4. Are we all right with that so far? Okay, not awful. Let's ask a couple more questions. We have this later, but we'll come up to that. Would you expect, based on structure, would you expect this thing to be polar or non-polar? Tell your partners. Okay, I heard non-polar from almost anyone I heard, and that is correct. All right, what if I had this angle right here? I meant to change colors. What would that be? I know I can't read your lips. It is 109.5. 109.5. Okay, 109.5. I was sitting here and Blaine says he's got to memorize the names. And Brown says I need to know the angles. And everyone, you're in those same boats. You need to know the names and the angles. Now, you don't have to know every angle, but you better know linear. That one's easy, 180. All right. Then the next one's 120. That's for your trigonal. Then your tetrahedral is 109.5. Like those ones you should absolutely know. So what's that? Yeah, there's lots of 90s and 120s in the octahedral and the penta bipyramidals. But all right, so we have that information. So the last part of this would be to know number of sigma bonds in the molecule and number of pi bonds in the molecule. And it's way easier than you think.
Is the sigma just the S bonds and the pi bonds just the
Kind of. But not really. Like the answer is yes, but I don't know that you're looking at it the right way that I'm going to tell you it is. Okay, here we go. Come on, Tom. Valence bond theory. You don't have to know a ton about this. Hybridization is a major player in this approach to bonding. And it's still a theory because it's really hard to observe this stuff, but it makes a lot of sense, so we assume it's correct. All right. There are 2 ways orbitals can overlap to form bonds between atoms. They are called sigma and pi. Sigma bonds are characterized by head-to-head overlap. Okay. So you would have like your S and your S, they would just overlap. And S's never have pi, so that is kind of correct for what Corbin was saying. All right, then an S and a P, a sigma bond would be the overlap here. Okay, and they'd share their electrons sort of there, whatever. It's head to head. I like to call this like a fist bump. Okay, so you like right there. You okay with that? Like a fist bump. Now, pi bonds are different. but it's okay. A pi bond is the side-to-side overlap of p clouds. And I like to refer to this as a handshake. Then I don't know if that will help you, but head-to-head overlap, like fist bump, side to side. How do you shake your own hand? Like shaking hands. Okay, don't worry about this sentence right here. I mean, you can, but the electron density is above or below the internuclear axis, not in the middle. Okay, so far, what should we know about this? We should know a sigma is head to head, and that a pi is side to side.
Are pi bonds double bonds?
Oh, why don't we go to the next slide?
So yes.
Well, kind of.
I love how straightforward chemistry is.
Okay, we'll get there. Oh, sorry, we'll get there in the next slide. Single bonds are always sigma. How about that? Sigma bonds, because sigma overlap is greater, resulting in a stronger bond and more energy lowering. So you need to know sigma's head to head, pi is side to side, and you need to know single bonds are always sigma bonds. Okay,
Sigma bond's always single bond,
yes.
so it works both ways.
Well, it doesn't necessarily work the other way. Here we go.
I said sigma bonds are always single bonds.
That works. That works. But in a multiple bond, one of them is a sigma and the rest are pi. So it doubles both. But then when you add the third, you have one sigma and two pi. I have no idea. I don't know where the names came from. Well, I mean Latin, but not Latin, Greek. Yeah, sorry, Greek, but I don't know what that really means.
Are you like in particular order, like one and then always sigma, one like a certain way, or?
Sigma, they're not really in a certain order, but like if you add CH4, you're gonna have 4 sigma. You just got to realize or memorize every single bond is a sigma bond.
Aren't you like, for like taking a probe on example, is one of them always sigma?
No, it doesn't matter. It'd be impossible to figure that out.
It seems like the kind of thing.
Yeah. Okay, so if we look here, if we looked in N2 and you were asked how many of each type of bond, there's one total bond. So there's at least one sigma, right? And then each second bond, second and third, would mean there was 2 pi bonds. So once you draw this out and it asks how many of each style, you count up every single bond, and that's your number of sigma bonds. Then you count the number of double bonds, and that's the number of pi bonds. If there's a triple, you add another one. So to summarize, sigma bonds are stronger than pi bonds because of greater overlap. A single bond is always a sigma bond. A double bond is always a sigma and a pi bond. A triple bond is always a sigma and 2 pi bonds. I should probably add here somewhere sigma equals head to head overlap. Pi equals side to side. Yep, that's my pi, I guess. My son Dallin, that a few of you know, maybe, he can wrinkle his forehead in like the most perfect pi sign you've ever seen in your life. It's incredible. The man has a gift. I don't know if he can anymore because he's now just like not as chubby as he used to be. Can I say that about my children?
Where's your child?
Are you recording?
I am.
I mean, unless he's gonna go watch this video.
Actually, Dallin does watch quite a few of my videos. Yep, because he just watches crappy YouTube and he subscribes to me, so I'm always on his list. And he'll come up to me like, "What is a Sigma bond?" I'm like, "Are you on drugs? Like, who watches this for fun?" I don't even watch him. He's probably my biggest viewer. All right, here we go. So how many sigma and how many pi in C3H8? Sorry, 6. Ooh, that means something. So why don't you draw it and then count up and see what you get. Ready, go. I'm going to pause this. Why? Why am I the way that I am? Why? I just don't even like myself. Okay. Yeah. Be like, what? Okay. What if we were to draw C3H4? I will tell you on this one, use a triple bond. Yeah. Holy, I take a lot of pictures of my children.
That's 12.
Three times 4 and 6, guys.
Oh, I don't know. There's some gems in here, I'm telling you.
That's why.
This is annoying me. Okay, well, I will spend my entire lunch hour trying to find that and put it on the group meeting.
That makes sense. That would make more sense than what I did.
Is that what you have? All right. This is the structure I get. All right. The central atom would be this one, correct? What is its structure? Linear. What is the angle? 180. Polar or non-polar? Non-polar. No, not necessarily. And it's definitely non-polar. It'd be slightly more polar than it wouldn't be, but it's still non-polar. Right. I'm sorry. Yep. Okay. Tell me this. Of bond A or B, which one is shorter? A, how come? All right, which one has a higher bond energy then? A. How many pi bonds? 2. How many sigma bonds? 6. What else have I not done yet? Everything. Oh, hybridization. Hybridization of the central carbon atom. SP. 1, 2. SP. If you were like, hey, I can do all that, then you have survived the last few days.
The end's gone.
Oh man, doesn't it feel good? Oh man, we have survived. No, it's you, not me. It's all you. Look at this. Oh well, never mind. That was so deep right there. By creating this arrow, I destroyed that arrow. I'm done. Okay, you have a crap ton on your test on Tuesday.
Is it on Tuesday? Woo!